We were formerly known as the RTB Raleigh, North Carolina chapter, one of the local chapters of Reasons to Believe. Reasons to Believe retired their chapters program in June 2024. Welcome to our March 2024 meeting. I have a follow-up to last month's presentation on the origin of life chemistry, and then we'll get into tonight's topic. After our February meeting, Nature magazine published a very interesting article on the current state of the origin of life chemistry from a materialistic worldview. I've downloaded and read this Nature magazine article, and I would encourage anyone interested in this topic to read it. This article appears to be written by those who only consider a materialist worldview when pondering the origin of life. They cite numerous problems with the popular views of how life on Earth started. This slide shows a list of what the article indicates that no scientists have figured out, and some of the major problems with three of the popular approaches to the origin of life question, including the prebiotic soup model, the RNA world model, and the hydrothermal vents model. In particular, the article comments that the sequence of steps to get from prebiotic chemistry to cells with genes is surprisingly different for each of these models, in addition to the problems with the models themselves. The following two articles provide some scientific commentary on the Nature article and on the hypernaturalist view of the origin of life. Both articles provide some good scientific perspective on the limitations of the materialistic worldview approach to the origin of life. If you're interested in reading these articles, send me an email and I'll be happy to send you the links. I also have a PDF copy of the Nature article that I can send you. And now let's get into tonight's topic, the design of the universe, part 1. Recent advances in physics and cosmology show us how incredibly profound the design of the universe is and how carefully staged it is for life in general and human life in particular. Are these just amazing coincidences, or is something else at work here? Because tonight's topic is rather technical, I'm including a few definitions of terms along the way. Here are our first two. Cosmology is the science of the origin and development of the universe, and cosmos is an orderly, harmonious, systematic universe. Next, we're going to discuss something known as the surprise principle. All right, so we're going to start with this surprise principle. And let me talk about this. So I'm going to give a generic explanation, then I'm going to give a more scientific explanation of this. So this principle, called the surprise principle, is something about evaluating evidence that is observed. And the idea here is it guides us to select the hypothesis that best explains the evidence and to reject the hypothesis that leaves us completely surprised in the face of the evidence. And I'll give a couple examples here in a minute. This is not, however, describing your unfamiliarity or surprise with a new idea. This is all about the observation of evidence. That's what the surprise principle is about. Now, let me give a more scientific explanation, definition of this. For two hypotheses, H1 and H2, the observation O strongly favors H1 over H2 if and only if hypothesis 1 were true, you would expect O to be true. In other words, O would not be surprising. If hypothesis 2 were true, you would expect O to be false. In other words, O would be very surprising in that condition. One other thing I'll mention here is this does not necessarily mean that H1 is true based on this principle alone, but that it is much more likely to be true than H2. And so we call this trying to get to the inference to the best explanation. All right, so I'm coming back in here. All right, so now let me give some examples of what we mean. I've got two examples here. Oops. There we go. All right, so the first example, I need to provide a little background. How many of you have heard of the game of poker? Just raise your hand. So you probably are familiar with this thing called a royal flush. All right, so a royal flush is a very highly ranked hand in poker. And in what I'm about to share with you here is I'm using 5-card poker, no hole cards, a regular 52-card deck, freshly shuffled. All right, this is not 7-card poker where the odds are actually easier. We're taking the most difficult case here. These are the odds of getting a royal flush in a 5-card poker sort of game, 649,739 to 1. This is a widely known fact. You can look this up pretty much anywhere. If you make this into a probability, you can see the percent likelihood of this happening. And there's more digits beyond that, but I figured that was enough precision. And so I took that tiny number and I converted it to with a scientific notation. So now we have 1.5 times 10 to the minus 6. That's the chances of getting a royal flush in a regular 5-card poker game. And as I'm letting more people in here, so that's what I'm pausing to do. All right, welcome everyone. Let me make this. I got multiple windows I got to deal with here. All right. So that's the background of this first example of the surprise principle. So now here's the application of it. Here's the observation. A player received 10 royal flushes in a row. All right, here's the probability of that. And of course, when you are dealing with probabilities, when you have independent events happening like this, you just simply multiply the probabilities. So you got 10 of those 10 to the minus 6 numbers that we had before. So the probability of this happening is approximately 7.4 times 10 to the minus 60. All right, that's a really tiny number. That's in technical terms there. Okay. All right, so we have two hypotheses here. The first hypothesis is the deck was stacked. The second hypothesis is this was completely by pure chance. All right, so given what you know about the surprise principle, first of all, let me back up. Does anybody here play poker or any game like poker? It's okay to admit that if you do. So here's the scenario. You're playing a game and this new guy comes in and he gets 10 royal flushes in a row. Now, are you, first of all, as another player in the game where you're presumably you're betting chips, let's say, in the game, are you happy about this? And what is your first thought? Is it hypothesis 1 or hypothesis 2? All right, what do you think here? So using the surprise principle, if you knew the deck was stacked, then the fact that he got 10 royal flushes would be probably disappointing to anyone competing against him, but certainly would not be surprising if you knew the deck was stacked. However, if you thought this was a purely chance situation, and this is just an example of random chance occurring, would that be surprising to get 10 in a row? That would be very surprising. All right. Now, just a little research, I looked this up and I went out and looked around for any occurrences where somebody playing a poker game in a widely known poker game actually got more than one royal flush. And I did not find any examples of people getting 10 in a row. In fact, the best example I could find was there was a tournament where one guy got 2 royal flushes in the whole tournament. That was the best example I could find. So surprise principle number 1 says, yeah, the deck was stacked. All right, that's the more likely explanation for seeing this observation. All right, now, the other reason I wanted to start with this one is because I want you to remember that number, that 7.4 times 10 to the minus 60. We're going to come back to that at the end. So just remember that number. All right, so that's the first example of the surprise principle. Does that make sense? Does everybody get that? Okay. All right, let's go to the second example. I don't need to provide any background on this one, so just going to get the screen to go. There we go. Here's the observation. The message, "Happy birthday, Dennis Martin," was observed written with seashells while walking along the beach. All right, that's our observation. Hypothesis 1, since my name is Dennis Martin, well, this is me here. I was walking along, I was visiting some friends at their beach property on my birthday, and they wrote this message using seashells that they collected. That's the first hypothesis. The second hypothesis is there was a storm 2 days before, and the message was caused by the natural forces of the wind, surf, and tides. All right, which one of those would be surprising? The first one or the second one? I think you indicate the second one, right? What we have here is an example. This is where my computer science comes in. What we have here is an expression of information, right? Happy birthday, Dennis Martin is an information type thing. We know that information comes from minds. It does not come from physical forces. We know that. And so hypothesis 1 would not be surprising at all, given where we are here. All right, so that's the surprise principle, just so you see how that works, and we're gonna apply that as we go forward. Now I want to switch gears a little bit and talk about the universe a little bit more. Actually, someone else is going to talk about it. I have to do a couple adjustments here so you all can hear the sound. And because this is now basically being broadcast over the internet, your picture and your sound might be slightly out of sync, but That'll just go on for this video. If you don't hear anything, please put something in the chat box, but we're going to listen to this.
From galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no stars, no life, no planets, no chemistry. Consider gravity, for example. The force of gravity is determined by the gravitational constant. If this constant varied by just 1 in 10 to the 60th parts, none of us would exist. To understand how exceedingly narrow this life-permitting range is, imagine a dial divided into 10 to the 60th increments. To get a handle on how many tiny points on the dial this is, compare it to the number of cells in your body, or the number of seconds that have ticked by since time began. If the gravitational constant had been out of tune by just one of these infinitesimally small increments, the universe would either have expanded and thinned out so rapidly that no stars could form and life couldn't exist, or it would have collapsed back on itself with the same result: no stars, no planets, and no life. Or consider the expansion rate of the universe. This is driven by the cosmological constant. A change in its value by a mere 1 part in 10 to the 120th parts would cause the universe to expand too rapidly or too slowly. In either case, the universe would, again, be life-prohibiting. Or another example of fine-tuning. If the mass and energy of the early universe were not evenly distributed to an incomprehensible precision of 1 part in 10 to the 10 to the 123rd, the universe would be hostile to life of any kind. The fact is, our universe permits physical, interactive life only because these, and many other numbers, have been independently and exquisitely balanced on a razor's edge. Wherever physicists look, they see examples of fine-tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. If anyone claims not to be surprised by the special features that the universe has, he's hiding his head in the sand. These special features are surprising and unlikely. What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence suggests that fine-tuning is necessary. How about chance? Did we just get really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way. A common-sense interpretation of the facts suggests that a super-intellect monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge.
If you've been in this group, you might have seen me present that before. Was any of that new for anybody, that whole concept of this fine-tuning and all those numbers? Or is this all old news for everybody? And if it's old news, that's okay. Let me get this back up here. All right, so let's move on. So since we're talking about the universe, how big is it exactly? And what does it look like? No one has been out at the edge and turned around, taken a picture and sent it back to us yet. We can't do that because it's a bit far. But I've got a really interesting video I want to play that talks a little bit about this part. And as soon as we do that, then we'll get into the meat of the presentation. So once again, I need to do these two things here so you can hear the video. And let's just go on here. All right.
I just want to interject that this is news that doesn't get old.
Yes, news that doesn't get old.
Have you ever thought about the enormity of God? The sheer magnitude of his power and size. It's a tough concept to wrap your mind around because God is spirit, so there's nothing physical about his stature. He can't be measured by meters or miles, time or space. However, it might be possible to catch a glimpse of what we can't see or touch by taking an imaginary journey through his biggest creation. This spacecraft will transport us to the edge of the observable universe, an estimated distance of 270 billion trillion miles. We'll travel at the speed of light, more than 186,000 miles per second. At that velocity, we could make at least 600 complete orbits around the Earth, in less time than it takes to eat a small bowl of popcorn. We depart on January 1st. Hurtling through space, we reach the moon in less than 1.3 seconds. Then 4.5 minutes later, we race past Mars. We continue on toward the gas giant planets: Jupiter, Saturn, Uranus, Neptune. And just 5 hours, 20 minutes after leaving Earth, we reach the dwarf planet, Pluto. Now we'll adjust our flight path for an angle nearly perpendicular to the planetary orbits. Behind us, the boundaries of our cosmic neighborhood quickly vanish. we have entered interstellar space, the great void between our solar system and the next nearest star. A year passes, then 2, 3, 4 years. Finally, on April 19th of the 5th year since our departure from Earth, we are momentarily blinded by the light of the Alpha Centauri system. 3 stars bound together by gravity. They are the closest stars to our Sun. We have traveled nearly 26 trillion miles, but we're just getting started. 10 light years from Earth, 24 neighboring stars glimmer in our wake. One of them, Tau Ceti, resembles our Sun. 100 light years, clouds of gas and dust in the Orion arm of the Milky Way surround us. 1,000 light years, the elegant spiral shape of our galaxy is clearly visible. Earth is located here. The Milky Way is part of a community of at least 40 galaxies drawn together by gravity to form what is known as the local group. For the rest of our journey, each point of light we see is no longer an individual star, but an entire galaxy filled with billions of stars. Our local group is adjacent to the Virgo cluster, a massive concentration of an estimated 2,000 spiral, elliptical, and dwarf galaxies that emit searing clouds of plasma and dust. This spectacular creation is the heart of a chain of cosmic islands, once shaped by the gravitational pull of 40,000 different galaxies. Collectively, they form the Virgo supercluster, one of the largest structures known to science. But as our view widens, this chain is quickly lost among countless formations of similar composition and size. For Virgo is a drop in a cosmic bucket that may contain as many as 10 million superclusters, each a slender thread in the large-scale construction of the observable universe. Our journey has transported us 45 billion light years from Earth to the outer limits of scientific discovery. A sprawling web of filaments spun from perhaps 2 trillion galaxies and stars more numerous than grains of sand on all the deserts and beaches of the world. So how big is God? He's big enough to create a universe with dimensions so vast they are beyond our comprehension. Yet in the words of the prophet Isaiah, he can measure it all with the fingers of his hand. The magnitude of God's power and size can never be reckoned by mathematics or physics, for he is omnipotent, eternal, and infinite. But if we explore the cosmos with open minds, not limited to theories of blind chance and the random collision of atoms, we discover a magnificent tapestry crafted by a consummate artist who once spoke all of this into existence from absolutely nothing, then revealed glimpses of his identity through the grandeur and design of everything he had made. And for anyone who has ever looked into a clear night sky, evidence of God's stature and character shines brighter than the light from 1,000 stars.
All right. So that picture there is a common conception of what the universe looks like at a distance. That picture you see there. No one, of course, has actually seen this because we haven't gotten out far enough to do that. But this is if you, and we're going to see another diagram like this shortly. So any thoughts on what you just saw?
Like, just like how is anyone even able to conjecture that that's what the universe looks like from that far out?
So yeah, the question is, how can anyone conjecture that this is what it looks like? There are deep space photos that have been taken with the Hubble and now with the James Webb Telescope that look a little bit like this. It's not as far out as this. This is like a wide angle view, this particular artist rendition here, but they are seeing this filament web structure. They're actually seeing that in terms of galaxies and threads of clouds and dust between them, and so it's a lot like this. So it's really interesting. All right. Well, let's get into it here. So go ahead.
It looks amazingly like the mycelium in the soil that fungus give us, and you know that similarity is.
Yeah, interesting. Yeah. All right. So for the rest of the time, let me make sure my mouse is in the right spot here. All right, there we go. So most of the rest of what I'm going to share is taken from Design to the Core by Hugh Ross. This is a 374-page book. It's filled with hundreds of citations from scientific journals and so forth. A lot of it from NASA, but a lot of it from other places as well. And so this is what we're starting to do now. When I started this process, I thought, great, we'll just do a nice summary of this book. I decided this had to be part one because there's no way to go through this. When I was prepping for this, I was talking to my wife about this before I did the first time. I said, there's just too much. There's just too much. I can't do this in an hour. So if you haven't read the book yet, I would highly encourage you if you want to go through it. But this is going to be a fast fly through about the first half of the book. And these are the things we're going to talk about. The universe's overall design features, our super galaxy cluster, Laniakea. The one thing he says in the book is that not all the astronomers have the same names for everything. So we're going to talk about the Laniakea supercluster, and then we're going to drop down into our galaxy cluster, which is Virgo, which they showed in the clip there. And then we're going to get into our local group, and then we're going to get into the Milky Way galaxy. There isn't time to go more than that tonight. So I will get into our solar system and our planet and our sun and all the other stuff in part two of this presentation. So anyway, that's what we're going to cover today. Now we have to have a few definitions. So a galaxy super cluster. This is from the book here. This is a grouping of galaxy superclusters. And then you have a galaxy supercluster, which is a clump of anywhere from 10 to 100 galaxy clusters and galaxy groups. A galaxy cluster this is again from Hugh Ross here, a gravitationally bound collection of a few hundred to 5,000 or more medium-sized, large, and giant galaxies. All right, so we're talking about really big stuff here. A galaxy group, a gravitationally bound aggregate of 5 to 100 medium-sized, large, or giant galaxies. And then a galaxy is a gravitationally bound system of stars, stellar remnants, planets, gas, dust, and dark matter containing over 100 million stars. The largest known galaxy contains 100 trillion, almost 100 trillion. So this is big stuff. All right. Now here's another rendition. This is taken out of the book. This is a graphic portrayal of this cosmic web structure. So we're seeing this again. This is a NASA, I don't want to say photo, a NASA rendition of it, I guess. You can get the idea of this web space sort of thing. Now, if you're a sci-fi guy, you're going, oh, the Borg cube. Well, it's not exactly that, and this is much bigger. But anyway, so this web sort of theme that you see is what the scientists who study this are coming up with, and we've now begun to see this in some actual telescope photos. All right, so we talked about the fine tuning a little bit. There's a few more comments about this in the book. The fine tuning that astronomers observe indicates that even very slight alterations to the universe's characteristic would rule out the possible existence of physical life. And this includes single cell life, multicellular organisms, creatures like humans, and highly populated and highly technological civilizations. I want to just mention something. All those scientists who were quoted in that first video, almost all of them are either atheists or agnostics. So that's what that's what the guys who think there's no purpose to all this, that's what they're saying. The numbers are finely tuned. It really gives the impression of design. That's what they're saying. The other thing I'll point out here, and he does a good job of this in the book, is on the second bullet point here, he stresses that we're not talking just about simple life or even advanced life like humans or other mammals. We're talking about a place that will support technological civilization, technological advances. I'll talk more about that when I get to a couple other spots here. So it's not just that there are intelligent animals roaming around. It's our Earth and all the stuff we're talking about here are designed so that technology can advance and there can be technological civilizations, not just really smart animals. All right. If a purposeful tuner exists, it makes sense that the deeper our search into the features of the cosmos, the more evidence of this fine-tuning the search will reveal. If no purposeful tuner exists, then a deeper search will reveal less and less specificity and intentionality. A fine-tuner's attributes and purposes will become either increasingly clear or increasingly vague. All right, and of course, go back to the surprise principle. All right, when you see these things that we're going to go through, what's the best explanation for this? Is it design or is it chance? And which would be more surprising, and which would be, oh yeah, of course, if it's a designer, this would happen.
Where's this quote from?
All of these quotes from about 3 or 4 slides back are all from Design to the Core.
Okay.
And in fact, let me just go back real quick here. I didn't say that, but I wanted to point out, I do have that on the slide here. Where are we here? There we go. So on that first bullet point, most of the following material in this presentation is quoted or paraphrased from that book. So all of that is coming from this book here, Design to the Core by Hugh Ross. All right, let me go back to where we were. And all of these images like this are taken from that book. Okay. All right, here we go. All right. Let's talk about the overall features. An abundance of evidence now indicates that if the cosmic mass, size, age, inflation, elements, and ratio of elemental abundances weren't structured exactly as they are, no one would be here to learn of them or ponder how they came to be. All right, so let's get some examples. Let's get some real examples here. This is all good, theoretical stuff, but let's get into examples here. All right, so let's talk about the table of elements. All right, we all know, we've all seen that. All of us probably have taken some level of chemistry at some point. So you remember in the video, the first video, it talked about if things happened, if the gravitational constant wasn't right or the cosmological constant wasn't right, the universe would have expanded too rapidly or too slowly. All right, so what he does here in the book is he says, well, let's take a periodic table of elements and let's see what would happen if there are different quantities of mass in the universe. So we have the mass we have now. What if it were just a little less or just a little more? All right, so if it were just a little less, this would be the table of elements. All right, this makes chemistry class really easy. All right, you got 2 elements here, hydrogen and helium. That's all you get. No one would be alive to take it, yes, and no one would be alive to grade your papers or any of that. I mean, this is what you would have if the mass of the universe were just slightly less than what it is. All right, so what's that?
We all talk fun.
Yeah, a little helium on our. Has anyone done that? The helium with the balloon to get your voice to talk funny? Yeah. All right. Now, if the universe were slightly more massive, this would be the table of elements. All right. Now, unfortunately, the book doesn't have the color version of these tables. I always prefer the color versions, but this is the way we have. So this is what the table looks like. And this table of elements, by the way, ends at 94. These are the naturally occurring ones. There are some man-made elements that are above 94, but this would be the naturally occurring elements. All right. If the universe were slightly more massive, I mean, more mass in the universe than we have now. And just as a reminder, here's the actual table of elements as it occurs now, all right, in our current universe. So you see, there's the full table. Again, not counting the man-made elements. Question?
Yeah, could you explain a little bit more what it means for the universe to be more massive?
More, okay, so what does it mean to be more massive? That means there's just more mass in the universe. So at the Big Bang, and we can go back, let me go back a few slides and I'll just mention that here. There's a spot here, I forget which slide it's on, so I'll have to go back here. Hang on just a second. All right, we won't play the videos. Well, I guess it's further back than I thought. I know I have this on here somewhere. I think I have it on here somewhere. I guess I don't. All right. I guess I have it. Maybe it's coming up. So I'm pretty sure I had something here. So basically at the Big Bang or shortly thereafter, we have a certain amount of energy, a certain amount of mass, a certain amount of rate of acceleration or inflation. All those parameters are there at the beginning. And so the point here is that if there was I know I have this in here somewhere. So the amount of mass, of course, when we talk about, we don't, if I go in the bathroom and step on the bathroom scale, I talk about my weight, because that's of course mass with the effect of gravity on this planet. So mass is just the amount of stuff, not counting, the weight of gravity to you have to multiply the gravity in to get pounds or kilograms or whatever.
So you're saying that when the Big Bang happened, if it didn't all spread out as far as it did, we would have more mass?
No, I'm saying there was the exact amount of mass in there at that time.
And this mass like hadn't been manifested into specific elements yet. It was just mass.
It's just the mass at this point before the stars start burning. Yeah. So yeah, but it's a basic measure. If you've taken physics, you're dealing with mass. I mean, all the classes start talking about that's one of the basic things you measure is mass. So I'm just going to call it the amount of stuff. I'm just going to say it that way.
Okay, so that instead the Big Bang generated a lot more stuff. That's what we're talking about, a more massive universe.
We're talking about the mass was all there and it's expanding. So the mass is all there. So
But
big,
it was a different amount of mass.
no, same mass. It's just now expanding. But it was so dense, it was, that it's like a black hole, except even more dense than that. So all the stuff. And if you talk about the conservation of energy, the principle of conservation of energy, mass is not destroyed. You can convert to energy or you can go to mass, but all that is still there. It's in a closed system. Now I say a closed system, we know there's someone intervening, but but the stuff, that's what happened. Yeah. So it's the amount of stuff. I'm just going to say it that way. All right. Where were we here? Oh yeah, we got to get to the chemistry. Here we go. All right. So any other questions on the chemistry? I'm going to get into what's missing here. So in the first two scenarios, with the really easy chemistry class, and then the other one that's slightly not as difficult, there's some things missing. Primarily, it's the life essential elements. All right. So if you look at the complete table, you see carbon, nitrogen, oxygen, sodium, magnesium, phosphorus. I've listed them all there. All of those are required for life. If you don't have those chemical or those elements, you can't get life. All right. I'll also point out that silicon is also missing. And if you look at the first half there, carbon is really a primary element, a necessary element for life. Silicon is really the chemistry of rocks. So you got the chemistry of life and you got the chemistry of rocks. If you want to get into chemistry, the carbon has 4 bonds, and there's lots of places for all kinds of cool things to happen. Silicon also has 4 bonds, but you can't get life from silicon. You can get rocks. And of course, silicon is very common on the Earth. And I would be out of a job in either of those other ones because computer chips are made from silicon. So anyway, so that's what would be missing if the universe had either slightly less mass or slightly more mass. And that's only one of all the things we could talk about. All right, now, it's not just that, though. Advanced life, whether as we know it or as physics and chemistry allow, requires a highly specified ratios of these abundance of these 94 elements. So it's not enough just that we have those 94 elements, but you have to have them in the right ratios to each other. So just imagine a series of equations with 94 variables, right? Just solve for that, right? You'd have to be really smart to put those equations together, right? And to think of them and get them to be in the ratios that they are. And we're going to talk about some of these ratios later on. But just this is the scale of the problem we're up against here. Equations with 94 variables, right? All right, now let's keep going. More than 140 different what he calls exterior features. And as you read the book, you'll see what he means by exterior and interior of the universe, including the values of the constants that govern the laws of physics, must fit within narrowly specified ranges. Of course, we saw that in the video. They didn't specify there's more than 140 of them, though. This reality reasonably points to a source with the capacity for intentionality, for deliberate, purposeful design and implementations. In other words, a creator who transcends the well-crafted cosmos. All right, now, I just want to provide a little background on this. It's 140 now, at least, but they didn't all know about all these a while back. So this is the history of these number of fine-tuned parameters you have to have in the universe as they've been discovered over the last, let's say, 40 years or so. And this is how many there are. So as you look at this, what's the trajectory here? Is it getting easier or harder for this to occur in a naturalistic, unguided way? What do you think? And this is only because we got better telescopes now than we had in 1989, right? And we've had, more, space missions and all that other stuff. All right, so just think of the trajectory of where this is going. All right, let's get into some actual stuff here. Supergalactic cluster known as Laniakea. Laniakea is the Hawaiian word for immense heaven. Seems very appropriate. Let me just read off some of these points here, even though you could read them yourself, because I think it's kind of interesting. It's positioned in an area of the cosmos that is least densely populated by galaxy superclusters. How convenient. It has a unique structure friendly to life compared to other known superclusters. Again, how convenient. The gravitational attractors in the Laniakea superclusters neighborhood are optimally situated and oriented for life in the Milky Way galaxy. Laniakea is one of the smallest, least dense, least globular superclusters. A globular cluster contains 10,000 to 10 million stars within a diameter of 10 to 150 light years. So the one we are in is just nicely situated, unlike most of the other ones. All right. Large, more dense galaxy superclusters are tightly packed together and are inhospitable to physical life due to intense deadly radiation and strong gravitational disturbances. All right. These also exert powerful gravitational attractions that can disturb the long-term stability of galaxy clusters and galaxies even beyond their own boundaries. So when there's a lot of stuff there, there's a lot of gravity going on, and anything that's nearby is going to be affected by that. All right. That's true at this level, and it's also true at all the smaller levels we're going to get into. No superclusters of galaxies are located near enough to our nearby superclusters, and Laniakea in particular, to pose a threat to life or the possibility of life here. All right? So it looks like someone's cleared out a little space for us. However, if the entire observable universe were as devoid of galaxy superclusters as our immediate region, the universe would not be conducive to life at all. So he uses in the book this term just right a lot, because there's a lot of things that are just right. All right. We have the right mix of uniformity and versus non-uniformity, and homogeneous versus non-homogeneous. So you have to have all of that, but we're at the supercluster level, we're in kind of a special place. And this is what astronomers have discovered. All right. Let's keep going.
Dennis, this is Grace.
Yeah.
Could I ask a question on that second bullet?
Yes.
So I understand that our region is lacking compared to others, but it's not clear to me what the implications are if other regions were also as empty? What about that would have such a direct impact on us?
He does explain that in the book, and I got my Kindle here. I'm going to refer to the section in there. Because I don't know the exact answer, but when I read it, I'm going, oh yeah, because he's got a lot of math in there. So give me a second, and I will pull that book up on my Kindle here.
Okay.
Yeah, that's a great question. When I read this, I'm going, man, yeah, how do they know that? There we go. Get back to, give me a second here. I should have had this, I should have had it queued up. Actually, I've got a physical copy right here. You want to grab the physical copy? We'll see which one I can get faster here. All right, here we go. Design to the core. All right, so I've got them both here. So this is the book, Design to the Core. All right, so I'm going to go to that section on the Laniakea. I'm actually going to all right, we're way in the front here. Here we go. Laniakea supercluster. All right. So let me actually get to there's a whole bunch of other stuff that's in this chapter that I just skipped over because it's just too much. Okay, one of the things he talks about here is he's calling it cosmic ray detection. Cosmic rays being coming out of other places in there. And he's talking about electron volts and kinetic energy. Let me just keep going here. I would have to refer to the book because there's just too much stuff here. It's in this chapter on the Laniakea supercluster, chapter 4. Let's see, where are we here? There we go.
Okay.
I would just say refer to the book, and I may have to default to that answer for other questions that might come up. But when you read through it, it's like, oh yeah, okay. There's just other physics going on and it goes to the point of you need the right mix. You need some of the thick stuff and some of the thin stuff. But if it's all thin, then there's not enough gravitational thing, and you go back to the video where it's things there's not enough gravity, stuff expands too quickly or too slowly. Yes, Jim.
One of the things I think involved in this is the effect of star growth and the proximity to small dwarf galaxies contributing to larger. It's a growth system of galaxies. It's beyond my understanding, but that's one of the things he talks about.
Right, he does, and I didn't mention that in those. If a couple of previous slides, I talked about medium, large, and super large galaxies. There's this other thing that he brings up all the time about these little dwarf galaxies that have a role. And to your point, Jim, that these little dwarf ones, there's a bunch of these around too, and they have effects. So it's all very intricately woven. That's all I can say at this point. And I'll say this now, I'll say it at the end. I highly recommend the book. But if you get the book, don't be in a hurry because it's extremely dense. There's a lot of material like on every page. Okay, let's keep going. To some observers, the shape of Laniakea resembles that of a stick insect or a praying mantis, which is kind of interesting. But the main point is this is unlike most of the other superclusters, which are either spheroidal or ellipsoidal, with their galaxy clusters and groups jammed tightly together. So ours happens to be stretched out a little ways, and this is at the supercluster level. All right. He talks more about the filaments here. These long, thin, spindly filaments. Again, think about that big web picture we've seen a couple times. Are crucial for the potential of hosting advanced life. Just enough density to matter to fuel and sustain a certain rare galaxy type, which we'll get to tonight, a large symmetrical spiral galaxy for several billion years. Because the filaments are long and well spaced, it's possible for a galaxy within one of the filaments to avoid the distorting and other disturbing effects of gravity from these other three galaxy clusters within Laniakea. So you've got gravity, you've got radiation happening, you got all kinds of stuff happening. And as these things move around, gravity starts to affect things, and We'll see more about what they call tearing in a minute. So it's just really interesting that ours, based on all the discoveries the scientists have made, it's like ours is a little different. It's like, interesting. And again, I'll refer to the book because there's a lot more detail than I have time to even go in. Now let's drop down a level into the Virgo cluster. All right, so this is the cluster of galaxies that ours is in. Most galaxy clusters have a core with a lot of stuff in them, but apparently ours is a little different. Ours is disc-shaped rather than spheroidal, if I can say that correctly. So disc-shaped meaning it's kind of flat as opposed to like a ball. All right, and it's much less dense. It also has a filamentary structure, allowing our little group of galaxies to sit well apart from other galaxy groups. All right, so that's within the cluster. Now let's drop down into the local group. This is the group of galaxies right near us. There are no giant ones, only two well-separated large ones, and only a few, here's these dwarf ones coming in, these few dwarf elliptical galaxies, none of which are large. All right. This scarcity and relatively low mass of such galaxies in the local group allows for structural longevity. All right, so things are stable. There's not as much gravitational pull in all different directions. In other types of local groups, most large spiral galaxies are being gravitationally torn apart because of their location among high density population. I'm going to show a picture of Milky Way coming up when we get to Milky Way and where we sit. And there was in one of the videos, there was a spot of that. Here's where Earth is. We're going to drill into that because that's important. All right. Our local group density. Our local group has the same diameter as the Virgo cluster, but of the core, but 50 times fewer galaxies. And our local group's core is empty. This is unlike the cores of all other known galaxy groups, which have giant and all these galaxies here. Because of this empty core, the two large galaxies are situated far from each other. So it's just an interesting observation. So he says this, the unusual characteristics and history of our local group have allowed for the Milky Way galaxy to maintain its central bar and highly symmetrical spiral arms. By the way, there's a picture coming up, with only a few spurs and feathers between them throughout the past 10 billion years. New study shows that the stability of this spiral structure has been maintained for many billions of years, primarily because our galaxy, I love this, has maintained a strict diet. It has consumed dwarf galaxies of the just right elemental composition and just right mass at a just right rate. So when galaxies, as they move around, of course, the big ones have a lot of gravity, and if there's other galaxies that get a little too close, they'll get subsumed into the big one. When I gave this presentation at NC State, there was a business major in there, and there was a section later on where I used the word merger. And I said, yeah, just like a business merger, except bigger and more violent. All right, so you're going to hear that word merger coming up here in a little bit. All right, so let's get into our Milky Way. All these are quotes from the book here. Our Milky Way galaxy possesses dozens of unusual and unique features important for advanced life, characteristics observed in no other galaxy among all those carefully studied by astronomers. The most important of these include its mass distribution, stellar populations, halos, disks, spiral arms, feathers and spurs, catalog of elements, merger history, and supermassive black hole. Even the galaxies considered similar to the Milky Way proves starkly different. All right, so there's a lot of stuff that's just unique about ours. All right, and in fact, this is where the merger thing came in. All right, so here's a picture. I should say it's not a picture. This is from NASA. This is them showing us what the Milky Way would look like if we were like vertically above it, looking down at it, or maybe underneath, looking up. So you see, there's a core of a lot of stuff in the middle there. There's this bar structure. It's almost like a dumbbell or a barbell kind of thing. And there's a couple things out at the end where it's a little thicker. And then you got these spiral arms coming out. All right, that white dot there is where our solar system is. So you'll notice it's in between two of the major arms there. So we're in a not really crowded place. And because we're in between the two arms, and you'll see this coming up, the gravitational forces of the arms on either side of us, we're kind of in the middle. So we're not getting torn. We're kind of in between where their gravities would affect. So we're exceptionally well placed in this. And that's one of the things we're going to talk about. So that picture there is where we are roughly in this. And if you look at this picture, it's a really nice, beautiful spiral structure. It really is. All right. So these are some of the unique characteristics. The ratio of the stellar mass to the total mass is lower by a factor of 2 than is typical for other local spiral galaxies. We have a much smaller disk scale length, that's the stuff in the middle there, that is typical. The observed features of the outskirt stars indicate over the past 10 billion years, the Milky Way has experienced no merger event with a galaxy as massive or more massive than 1 billion solar masses. So we got some big numbers going on here. By contrast, other spiral galaxies of the same approximate mass as the Milky Way have experienced several major mergers during the past several billion years. Throughout the past 10 billion years, Milky Way has suffered no merger events of sufficient magnitude to alter its spiral structure in any life-threatening manner. It has accreted, I mean, it's gained sufficient streams of gas and sufficient number and rate of low mass dwarf galaxies to sustain its spiral structure. Unlike other known spiral galaxies, the Milky Way sips rather than intermittently gulps. Okay. And I'm going to show some pictures of other galaxies that look like similar to the Milky Way, and you'll see the difference here in these photos. And the key thing is a spiral structure and stability are essential to the possibility of hosting advanced life. So other kinds of galaxies just can't host life at all. It has to be a spiral. All right, now, if that wasn't enough, the angle at which the arms come off of the center is also critical. All right, so this is the same photo, and this is a diagram from the book where you see these angles coming off there in the addition up to the picture there. All right, so if the pitch angle is smaller, that means the more massive the central black hole. So all these galaxies have a big black hole in the middle. A high mass central black hole will generate deadly radiation throughout the galaxy and beyond, of course, making it life prohibiting. The closer the arms are to each other, the planets between any of the two arms would be too close to the powerful ultraviolet radiation emitted by the young giant stars and would be subject to gravitational disturbances from the molecular clouds in those areas. However, if the pitch angle is too wide, then the symmetry of the structure is more easily disrupted by other galaxies as they move around. And yeah, so again, the pitch angle has to be just right. And as it turns out, in our case, it is. Amazing. All right. Galaxies without spiral arms are non-candidates for life due to the high density of stars. You get erratic planetary orbits, frequent bombardment, and the bombardment means, comets and asteroids and stuff hitting planets. These also grow very large supermassive black holes that generate deadly radiation. Given that the existence of advanced life requires a long, continuous history of less advanced life, a galaxy that can possibly host advanced life must maintain its stable spiral structure for at least several billion years. So it's not enough that life can occur now. The prep for it has to have been laid out, is really what the point is. All right, here's another one. Galaxy color. Most galaxies are described as either blue with predominantly young hot stars or red with predominantly older cool stars. The Milky Way is neither, but it's green. It has both blue and yellow, but not many red. And the green ones are rare, but the exact kind necessary for life, as it turns out. It lacks many of the very old or the very new stars. It's in the middle of a transition from a star-forming galaxy to a stable galaxy. It no longer predominantly is building the components for life, and you see them listed there, but to sustaining advanced life. All right, one more. Well, there's more than one, but here's another one. Luminosity. Luminosity is the amount of light coming off of the stars in the galaxy. The Milky Way is also underluminous compared to other galaxies of its size and mass, which protects the Earth from excessive radiation. All right, because all these stars are emitting all kinds of radiation. But also, this low luminosity allows astronomers on the Earth a better opportunity to explore the Milky Way and beyond. All right. Now, I have lived in big cities like LA and New York City. I have visited Chicago and Houston and other big cities in the US and London and other places. And if you're downtown in one of these big cities at night and you look up between the buildings up at the sky, you're not going to see very much in the way of stars, assuming that it's a clear night, because there's just too much light pollution in the city. If you want to see the stars, you got to get out away from the city. This is true on a galactic level as well. Our Earth is in a very special spot, not only to protect it from all the radiation, all that stuff, but also to give us a better view out. It's really interesting that both of those things are occurring. It's safe for life, and it's in such a position that we, as intelligent life on this planet, can see out and just make these discoveries in the first place. All right, let's talk about black holes. Supermassive black hole, just about every galaxy has one. But ours, it's again mass, so all this physics about mass, is exceptionally low, which is extraordinary and unexpected. This is not like the other similar galaxies. The black hole in the middle of ours is much less massive, which makes radiation coming off of it it's not as strong for us. All right, so here's an overview of a whole bunch of things about the Milky Way. I won't read all of these. You can look at this. We've talked about that, most of these. I'll just put this list here and leave it there, and I'll let you look at that for a minute and just see how unique our Milky Way is. Now, the term spurs and feathers means these other little groupings of stars or galaxies kind of along spur or feather. There we go. Just everything is not just like a straight line. You know, these web. If you go back to the picture of the web thing, it's not exactly straight lines with a grid. Everything kind of turns. You know, they're not straight lines. They're curved. And so the spurs and feathers are these little tiny extra little pieces that are in various parts of the galaxies and the clusters and everything else. All right, I'm going to move on to the picture here of this next picture. I'm trying to get my mouse to behave. All right, there we go. These are photos actually of other spiral galaxies that these are taken with Hubble or other space telescopes. You can see all this the listings there. And it has their names and what their numbers are and all that other stuff. If you look carefully at those, and I realize there's a lot of them, and so each one's a little smaller, they just don't look as perfect as ours does. If you just look at the shape, look at the way the arms are formed, look at how many arms there are, how smooth the curve of the arms is, it's just different. These other ones, these are the ones that are similar to Milky Way that have been discovered, and yet they're all, by comparison, a little wonky, you know? And if you have the book, of course, you can see these a little bit better because they're in the book here. Okay, let me talk about a few things, and now we're going to start to get back to some of the things we said at the beginning. In addition, there are 4 compendia that he refers to in this book that you can download from the website, and there's the link to where you can get those. So the first one, part 1, talks about those 140 parameters. It lists all of them that are necessary for life in the universe. That's just life in the universe at all. The second one is the 402 parameters that are needed for physical life, for intelligent physical life. All right, so not just one-celled animals, but something more interesting. All right. The third one, and this is where we're going to talk about some math here again. These are the probability estimates for features required by various life forms. All right. So in this one, there are 501 parameters listed that are necessary for life on a body, it says, but it would be a planet, right? So the probability for all 501 parameters occurring is 10 to the minus 333. That's the probability of getting all of them to occur at the right time, in the right place. However, how many possible planets are there? Well, there's 10 to the 22nd possible life support bodies in the observable universe. So this is only the part that we can see. So, you know, there could be more, but this is what we can see. So if you do the math here, you subtract the 22 from the 333. And what this means is there's less than one chance in 10 to the 311 that even one such life support body, I'm going to say planet, but the official term is life support body, would occur anywhere in the universe without invoking divine miracles. All right, so let's go back to our royal flush example. Getting 10 in a row, we said was how much? 10 to the minus 60. This is saying 10 to the minus 311, one chance in 10 to the 311. So, or you can say 10 to the minus 311 of that occurring. So which is more likely to occur? Getting 10 royal flushes in a row, or this? Well, clearly the 10 royal flushes in a row is more likely than this because it's only 10 to the minus 60, whereas this is 10 to the 311, or one chance in 10 to the 311, or one over that would be 10 to the minus 311. So the 10 royal flushes would be more likely to occur than this. Life on one such planet. Any kind of life. This is like simple cell life, whatever. All right, that's all pointed out in compendium number 3, or compendium number 3. In compendium number 4, now this says, let's talk about the requirements for advanced life. 159 parameters, the chance of that happening, 10 to the minus 412. Maximum number of planets in the observable universe that could support advanced life. So it's not just the potentially like a single cell animal, slightly less, 4 times 10 to the 21st. Remember the previous one was 10 to the 22nd. So do the math there. Less than one chance in 10 to the 390 exists that even one planet containing the necessary kinds of life would occur anywhere in the universe without invoking miracles. Advanced life like us. All right. All right. So again, I go back to the poker example. 10 to the minus 60 is a chance of getting 10 royal flushes in a row. And now we're like way beyond this here, of this occurring without a divine intervention, without somebody stacking the deck, as it were. All right. So if we talk about the surprise principle, let me go back here. Let me just go back to this, just so the numbers on the screen. All right. So would you be surprised if this actually occurred randomly? Given that there's only 10 to the 21 planets it could possibly occur on, and the chance is 10 to the minus 390 when you do the math. If there was a designer, would you be surprised? No, not at all, right? All right, so that's the point of this summary point, is that the surprise principle, if you use the surprise principle, the scale of these probabilities for the complex requirements of advanced life, what sort of hypothesis would make sense of the increasing number of observations we make where the parameters seem to be finely calibrated for life, advanced life especially. All right, so just doing the math, for all of you who like to do math or at least are aware of the math, your odds are better of playing poker and hoping that you get 10 royal flushes in a row are much, much better than this. Okay, in part 2, we will cover these things, smaller than galaxy clusters. I do have some recommended reading. Of course, Designed to the Core is the book we're talking about. There are 2 other books that Hugh Ross has written, which deal with a lot of the same stuff, but this is the newer version. I will also recommend these 2 books, which are not Hugh Ross books. These are excellent books. Blackwell Companion to Science and Christianity. This is a good reference book to have. Anything relating to science and Christianity, great reference book. And I would highly recommend also Return of the God Hypothesis by Stephen Meyer. I've read that one. It's also not an easy read, but it's well worth reading, and it's understandable. That's the key thing. It's understandable. As is Designed to the Core. It's just there's a lot of math in it. But the examples are understandable. The way he writes it is understandable. All right, I've got a couple other recommended reading things, and if you want me to go back and leave something up on the screen for a while, I can do that. Just a couple other articles you might want to read, and one of them including the second bullet point there. We all know about, and we'll talk about this when we get into the planets and the exoplanets. We know about everybody's search for water, because water is one of the things you need in a habitable zone. But he's also explaining that you have to have a galactic, there are habitable zones at a galaxy level and a super or a galaxy cluster level, in addition to a solar system level. And not everybody's thinking about that. And we've covered some of those points here. So it's not just that. And when we get to the part 2, where I talk about the planets, we're going to go into the fact that it's not just a water habitable zone. There's 11 other zones that have to match up too, ultraviolet and a bunch of other ones. So it's great that they're looking for water, but that's only one, and you need more than that. So anyway. Okay, so that's all I have from a scientific standpoint, but I have one other announcement that I think will be of interest here. RTB, Reasons to Believe, the organization we're working with, has decided to retire the chapters program at the end of June. And what that means is they will no longer create new local chapters or maintain oversight of existing chapters. So what that means for us is business as usual. We're going to keep doing what we're doing. It just won't be an RTB chapter anymore. So the sign that I have behind me, I'll have to take down. We won't see it. We will keep doing what we're doing. We'll still keep talking about science. We'll still be talking about archaeology and all the other things we talk about. We just won't do it because RTB won't be doing chapters anymore.
And we won't be able to use the RTB name.
We won't be able to use the RTB name. However, we will still have access to RTB scholars. I can still request them to speak. We can still reference their books. We might even get some of them to come in on Zoom. All of that is still possible. It's just they're not going to run a chapters program. They've got some other things they're trying to do, and this is, a different. Things have changed from when they first started the chapters program to now, and so they're changing their focus because they're in a different place in their lifespan, in their business lifespan. So chapters are not as essential for what they're doing, but we will still keep doing what we're doing. There is, however, a global virtual chapter, which has been set up. The first meeting was a month ago or so. And this is an attempt to get chapter-like participation, but all around the world. And so they're doing it on different days and in different time zones. So sometimes it'll happen while we're sleeping, and sometimes it'll happen while we're awake. But you're welcome to look at that. I did attend the first one. Hugh and Kathy Ross were on that one, and it was a great Q&A and all kinds of stuff. And they talked about design to the core and some other things. And so there is a recording of that. You're welcome to look at that. So that's what's going on here. So we will do business as usual through June, and then after that, we will keep doing what we're doing. We just won't be able to call ourselves RTB, an RTB chapter. Okay. Any questions or comments?
I just wanted to say I really appreciate your presentation. And I was thinking about the question that Grace asked. God allows us to see things and discover things, not just in astronomy, on the planet micro level and so on. And it's, without invoking the God of the gaps attitude, I'm saying that, we've learned a lot about our galaxy, and the safety of it is, if you want to put those terms together, because of what we can see in other ellipsoid or globular galaxy clusters and giant massive radiation mills that blare out things. But we're able to recognize that we're in a safe zone. And so, and that's just looking at it from a close-up view. But long-term, we don't know what's coming. We don't know what else out there might be of value to us. Now, that's just an observation. I don't know, but that's one of those are two of the things that I'm thinking of when that question was posed.
Great, thanks.
I was just thinking of the Neil deGrasse Tyson quote about the universe is trying to kill us. But if you look at this, actually the universe is trying to keep us alive.
Well, yeah, so it's interesting that you mentioned that Neil deGrasse Tyson book. It's actually in the first part of this book. And so when I first got this, I put together a little video where I took that where Neil deGrasse Tyson actually says that. There's a video clip of him saying that, and then I put it right up against Hugh Ross talking about, hey, it depends on who's holding the scalpel as to whether this is a skilled something for healing or something for destruction. And so there's a really nice juxtaposition of Neil deGrasse Tyson, but he actually references that quote in the book. That's one of the first footnotes in the book. But Neil deGrasse Tyson's point is, if you look at all the rest of this stuff, it's very inhospitable to life. And what he doesn't say very often, but he has said, is, but Earth is special. So, but he doesn't want to talk about that too much, because then that leads to implications of, well, why is it special? So, all right, anybody else?
Dennis, it's me again. Thank you
Yes.
for the presentation. I thought that was really interesting and a great summary. I have two questions.
Okay.
The first is, I thought it was interesting that you pointed out that the macro structure of other spiral galaxies appears to be less perfect
Less
than
optimal,
our
yeah.
own.
Mhm.
And I wonder if is that just an anecdotal observation, or is there something behind that Dr. Ross suggests in his book? And then number two, and not to open a can of worms, so we can talk about this at another time, does RTB have a stance on life outside of Earth and whether that exists in the universe?
Yes, so let's talk about the first one, talking about the spiral, I'll say suboptimal other galaxies. So he does talk about that, and what scientists have seen, at least in that section of the book, is because of those arms being not exactly perfect, you do get these gravitational issues happening, and of course it makes it inhospitable to life. He does go into more detail there in the book, so I would just refer you back to that chapter. He does do that. As far as life elsewhere, I have heard a couple different things. One of the questions, and this is more general, is if there's life elsewhere, and by that I'll say intelligent life like us, as opposed to amoebas, for example, does that do anything to the gospel or the message of the Bible? That's one question. And then the other question is, if there's life like us, wouldn't that be cool? Wouldn't that be interesting? So first of all, I don't think it doesn't affect Christianity, because I think Jesus would do what's necessary for these other people wherever they are. But the question more about RTB is, one of the things Hugh Ross says is, all of these, he talks about the age of our solar system and our star and all that stuff. All of the things, and he talks about it in the book, he says all of these things that are now occurring here happened at the earliest possible moment that they could occur. He says, if there was other life, it would be at best no further along than we are, but probably not even as far along as we are, if there is any at all. But of course, if you go to the math here, the chance of that happening without a divine intervention is, of course, almost zero. But so I think their position, RTB's position, is there probably isn't life, but I don't think they can rule it out entirely. I mean, there could be stuff we don't know, because there's definitely stuff we don't know. So that's what I know of their answer.
Okay, thank you. I appreciate that.
Yes. Anybody else?
This might be a read the book answer to the question, but so I'm just trying to understand the whole probability of all the parameters lining up.
Yes.
That leads to applying the surprise principle. And with the poker example, that's pretty clear, because you have the shuffle deck as your bank of possibilities, and you get a certain number of cards.
Mm-hmm.
But as far as what parameters are present in a universe, it's not as clear that there's a deck and each card has an equal probability of being passed out.
Yes.
So yeah, do you know how they calculate the probability of that combination of parameters?
Yeah, it's a great question. Hopefully you all heard her question, but I will repeat it. So how do they, specifically RTB and Hugh Ross, how do they calculate these parameters? How do they come up with, well, this one would occur this percentage of the time, and then that one, of course. And they have, in some cases, they are estimates, based on what we see in the earth, as far as like minerals and what's the ratio of nitrogen to oxygen in the atmosphere, those kind of things. We can measure some of those things. So we know that, for example, you need a certain amount of oxygen in the atmosphere. There's lots and lots of other ones, and they list them in those 4 documents I described. Some of them are just being conservative estimates, but some of them are actual data that people have figured out. So as you know from statistics, when you have lots of probabilities, you can just multiply them all together, and even if they were not terribly, let's say they could say that it was a 1 in 10 chance for some of these things. Even at that level, you're still going to get, by the time you put them all together, you're going to be 10 to the minus a whole big number. So, and the other thing I'll refer to is that one chart where I showed in 1989, they knew about this many of them, and now in 2006, they knew about this many more. So they keep having to redo the math because they're keeping discovering, life isn't going to work unless you also have this. And they keep coming up with these, and not just Hugh Ross, but NASA scientists and all these other guys keep coming up with more and more things that, for life to happen, you have to also have this. And these are not, and some have calculated how likely those are, or how hard they are to get. So some of them are actual measurements, some of them are just conservative estimates because that's all they can go on. Yeah, good question. Anybody else? And you notice I'm not claiming to be an astronomer here, so that's why I keep saying it's in the book. But that's another way of recommending that you read the book. But I will do a part 2 of this where we go into the other things. For example, I have been tracking, you can go to NASA and track how many exoplanets have been found. These are planets that are not in our solar system, but they've looked for. And the number they actually keep a counter on there. So I was going to put that in the previous presentation, or when I did it last month, then I realized I had too much material. So I will update that because I had all the numbers from whatever day in February that was, but there's maybe they've discovered a couple more. So I try to keep it current when I get to that one, it'll be current with whatever it is when I do that version of the presentation. Anybody else?
I'll just say thank you, Dennis.
Oh, you're welcome, Doug. Thanks. Appreciate it. Doug is our vice president of our chapter.
For the next 2 months.
For the next, for the next 2 months, till that goes away. Yes. All right then. Well, let's close with a word of prayer. Father, thanks that you are amazing, and you have done work we can barely comprehend in the universe, and all of these structures that are there, and all these big things, these really big things. And yet you care for each one of us, and you have prepared a place for us here, and we know that you are also preparing a place for us in eternity. Thank you that you are so gracious to do this for us, so that you can have a relationship with us, and so that we can delight in you and delight in the things that you have done. Thanks for those scientists who have done all this hard work to figure out a lot of these things, or just notice that these things that you have done on our behalf. Thanks for how intricately we are made, in our bodies and our brains, and all our just how we are, in addition to how intricately you have woven this world together for us. And thanks even more for coming to be among us and live with us and show us how it's done, and experience the things that we experience. And by doing that in the person of Jesus Christ. So we thank you so much for all of this. Thanks for this chance just to get together and discuss a few things. And we ask that you bless each one of us as we go to do our other things as we leave here tonight. We pray in the name of Jesus Christ. Amen. Amen. All right, thanks all. I did have the recording on, so I will stop that. And if you want this recording, I will send out a post for that. Let me get to the stop here.